So in this video, I want to talk about section 9.3. 9.3 is really all about solving what are called differential equations. And namely, this is the kind of easiest type that we can solve that we haven't yet, called separable equations. Okay, and so in particular, we're going to talk about separable differential equations, and I'll talk about what that means in a second. But differential equations are a application of calculus that gets used a lot in modeling. And so there's a course, differential equations, Math 2020, that you take after Calc 3 if you're a physics student or math student or engineer. And these get used a lot in different types of modeling. So what we're going to do is we're going to kind of take the easiest type of differential equations that we can study at this point. And those are called separable differential equations. And we're doing it at this point because section 6.5 is also about applications, and 9.3 is about applications, and we have everything that we need to know for both of those. So a separable differential equation, first of all, let me just say that a differential equation is something that you've already seen before. You just don't think about it as a differential equation. But a differential equation is just an equation with a derivative in it, and you're trying to find a function that satisfies a particular equation. You've seen this since Calc 1 in the sense of if I give you the derivative, say 2x plus 3, then you give me the function, and I can even give you an initial value, say f of 0 equals 7, then we know that the one and only one function that has both of these properties is the function x squared plus 3x plus c, where c happens to be 7, because f of 0 is c. So anyways, so there's a little bit of work to do there, but that's a Calc 1 problem, essentially. So this is something that we did in section 3.9. So this is section 3.9 in Calc 1. And so this is really that's the section on antiderivatives. And that's really all that this is when we're talking about differential equations, at least at first glance. So these are the first type of differential equations. And so if you have y prime equals g of x, where you have no y's on the other side, then that tells you that y is going to be the integral of g of x. And then maybe you're given an initial value like we were in this case. We were given this initial value, which if you're not given the initial value, then the only thing that you can do for the solution is to come up with a family of solutions, right? You'll always have this plus c there. But if I give you an actual value for the original function, then that uniquely determines the function. Okay, and so this is the first type of differential equation. We're not going to do any more with that. The next kind of step up is what are called separable differential equations. And separable differential equations are where you have y prime equals g of x times h of y. Okay, so here you have two functions and they're being multiplied. One's just a function of x, one's a function of y. And so what we're going to do here is we're going to change our y prime to dy dx. And then what we're going to do is we're going to get all the x's on one side and all the y's on the other. And so what I mean by that is that we're going to divide both sides by h. We're going to leave the dy over here, and we're going to have the g of x and the dx on the right side. Now, strictly speaking, what I've written is nonsense. Dy dx is not a fraction. Dy dx refers to, it's the limit of the difference quotients. It's the derivative. It's the limit as h goes to 0 of, limit definition of a derivative. But in a lot of ways, it behaves like a fraction. And this is one of the ways where it behaves like a fraction. So even though what I've written is nonsense, if I integrate both sides, then everything's fine. And it turns out that this is true. And the reason why this is true is that dy dx, if I have a function, let me just write this a little bit better. If I have a function y equals f of x, then the differential dy is going to be the derivative, so f prime or dy dx, times dx. So we know how differentials work from Calc 1. And that differential equation here, the dy is equal to dy dx, is why we're allowed to do this. Okay, it's why integrating both sides is legal, but having it the other way is not. So anyways, so these are separable equations. So let me give you a few examples here. So let's start by solving y prime equals 6xy. And let's add in that y of 0 is going to be, say, 3. Okay. And so I want to figure out what's the one and only one function where when you take the derivative of the function, you get 6x times the original function. Okay, and I also have added that I want when x is 0, I want y to be 3. So when I write y of 0 equals 3, this means that when x is 0, that implies y is 3. And so what we're going to do here is we notice that we have a separable differential equation, which is the only type we're going to deal with in this entire course. And so we're going to start by writing y prime as dy dx. In fact, let me just erase that and write that in. Okay, so dy dx. And what we're going to do then is just rearrange both sides. And so we're going to get 1 over y dy is equal to 6x dx. And then I'm going to integrate both sides. I integrate in that step just so that I never have a step that's incorrect. And now when we integrate 1 over y dy, we're going to end up with the natural log. Technically, it should be the natural log of the absolute value of y. I'll explain why we can get rid of the absolute value in a second. And the integral of 6x is, of course, I was going to say 6x squared, but it's not. It's 3x squared plus c. And now our goal is to solve for y. And so we know that there's a few different ways to do this. Before we solve for the constant, what we're going to do is we're going to exponentiate both sides. And we're going to get the absolute value of y is equal to e to the 3x squared plus c. And then we're going to do a trick. And the trick here is going to be that if I write e to the 3x squared plus c, that's e to the 3x squared times e to the c. And remember, c doesn't stand for a specific number, at least not yet. When we use our initial value, we'll get an exact number. But for now, c just stands for an arbitrary constant. And when I take e to an arbitrary constant, I get another arbitrary constant. So I can actually think of this as c e to the 3x squared. And then the final thing that we can do is we can drop the absolute value signs, and we get that y is c e to the 3x squared. And there's two reasons for that. One is that if we have a negative value for y, we could just figure out what the value of the constant is. But the other is that we know that our y value is going to be positive, at least near 0, because when we plug in 0 for x, we get y equals 3. Okay, so we can drop the absolute y value because y is going to be positive near this point, x equals 0. And then the final thing to do is to figure out what is our c. Okay, and so when we do that, we know that when x is 0, y is 3. So if x is 0, that tells us that y is going to be c times e to the 3 times 0 squared, which is 0, which is going to be c. And then we're told that that should be 3. And so from this, we get that c is equal to 3. And therefore, the one and only one function that fits both of these criteria is y equals 3 e to the 3x squared. Okay, and that's the only function that's going to satisfy both of these conditions at the same time. So it's what I mean by both these conditions is this differential equation and then this initial value. Okay, so it's going to satisfy both of those at the same time. So that's separable differential equations. Let's do one more. Let's look at y prime is equal to 4 square root of y. Okay, so something like this. So if we have y prime is equal to 4 square root of y, I'm not going to give you an initial value. We're just going to solve this differential equation. And there's no x's on the right side. So we have dy dx is equal to 4 times square root of y. And then we can divide both sides by square root of y. So 1 over square root of y dy is equal to 4 dx, and then integrate both sides. And 1 over the square root of y dy is going to end up being 2 square root of y. And the integral of 4 is going to be 4x plus c. And then we can divide both sides by 2. And we get that the square root of y is equal to 2x plus c. We don't have to divide c by 2 because, again, c is an arbitrary constant. And finally, we can square y. We can square both sides. So we got y is equal to 2x plus c squared. Okay, and here notice that the constants inside the function And so for different values of c, these will all be solutions. You can't bring the c out because then you get a different function, but you need to leave the c inside. So that's separable differential equations. One last thought, and this is something that I said last week and just something that I want to talk about here. I made a comment that e to the x is the only solution to this differential equation up to constants. And so if we were to do this, so I guess I'm squeezing in one more example here, but this is an easy one. dy dx is equal to y. This means 1 over y dy is equal to dx. And then we integrate both sides and we get that the natural log, the absolute value of y is equal to x plus c. And that tells us that y is equal to c e to the x, basically mimicking what we did in our first example. Okay, so basically mimicking the algebra here. So I'll let you fill in the details, but this really is true that if we look at this differential equation, y prime equals y, the only solution is going to be a constant times e to the x. Okay, so at this point, we're prepared to talk about that. Okay, but I think that's enough examples to go through the, I think there's only 3 homework questions in this section, but that's it. And we'll do a few more examples in class.